Welcome to today class of nonlinear vibration. So, today class we are going to discuss about the stability and bifurcation analysis of nonlinear fixed point responses. Particularly, we will discuss about the equilibrium points and their stability and about the static bifurcation points. So, in static bifurcation points we will discuss about this saddle node bifurcation, pitchfork and transcritical bifurcation. Next class we will study about these hop bifurcation points. So, in the previous class we have discussed about several nonlinear equations and in those equations how to find the equilibrium points. So, equilibrium points are points for which there is no or these will be the steady state solutions of the systems which will not vary with time. So, to obtain these equilibrium points we will not consider the terms containing the time. So, in different equations we can find the equilibrium points and we have to study their stability. So, in case of the to find the equilibrium points in different nonlinear equations. So, previously we have studied different types of methods, different perturbation methods, or directly we can use this harmonic balance method or other different types of solution methods to find the equilibrium points. So, after finding these equilibrium points we are interested to find, so what should be its stability, whether the obtained solutions is stable, unstable, or what will happen to the system as time progresses. So, in case of a stable system, for example, if we consider the simple spring mass system which can be represented by a Duffing equation also. So, if we are considering the nonlinear spring, so it can be represented by this Duffing equation. So, this spring we have considered it nonlinear. So, this equation can be written in this form, that is mx double dot plus kx plus, let me take a nonlinear spring. So, in that case it will be k1 x q plus c x dot equal to, if a force f sin omega t is acting on the system, then it will be f sin omega t. So, this is k, this is c damping and this is linear stiffness k and nonlinear stiffness k 1. So, in this equation, so first we have to solve the equation to obtain the equilibrium position. So, for example, the static equilibrium position, so for which x equal to 0, so will be the equilibrium position. So, by using several methods, so we can find what will be the response of the system. One may also solve this equation using numerical methods to find the solutions. So, after getting different types of solution, so we will find the stability of these solutions. So, to obtain the stability, for example, let us take a one dimensional equation. So, in this one dimensional equation can be written in this form, that is x dot equal to f x m, where m is the control parameter and f is the. So, to find the equilibrium position, the time derivative term, that is x dot, we have to put this x dot equal to 0. So, it will reduce to f x m equal to 0. So, if you solve this equation for different value of x, so that will give us the equilibrium position. So, singular points or equilibrium positions are the location in the state space where the vector field is vanished, and we can find that thing by equating this f x m equal to 0. So, we may have to solve a set of algebraic equation or transcendental equation or different types of equations to find this equilibrium position. So, to study the stability near the equilibrium position, so one may do this linearization. So, let for the control parameter m equal to m 0, the solution becomes x equal to x 0. So, if x equal to x 0 is the solution for this, then one can write by perturbing this solution, that means, so let this is the equilibrium position x 0. So, now, so what will happen next to x 0? So, if we perturb this thing, then we can write this at x t, that means at time t which is slightly away from this x 0. So, we can write this x t equal to x 0 plus y t. So, y t is the small perturbation if you take, then we can write this equation, previous equation, this x dot equal to f x m by this equation. So, y dot equal to f x 0 plus y m. So, now expanding this thing using Taylor series. So, one can write this y dot will be equal to f x 0 plus y m 0 plus d x f. So, that is the first derivative of this f at x 0 m 0 y, and one can neglect these higher order terms. So, neglecting the higher order terms. So, one can write this equation y dot equal to, as already this f x 0 y m 0 equal to 0. So, according to our assumptions here, f x 0 m equal to 0, which where we are getting x equal to x 0. So, this part is 0. So, one can obtain this y dot equal to d x f x 0 m. So, this matrix, that is d x f or this A, is known as the Jacobian matrix. So, by finding the eigenvalue of this Jacobian matrix, so we can study the stability of the system. So, after finding these eigenvalues, so if all the real parts of this eigenvalue are negative, then the system is stable, otherwise the system is unstable. So, let us take one example. So, in case of the, so before that let us see whether this linearization technique, so what we are finding, so whether this is valid for all the cases. And so, there is one theorem, that is by a Hartmann and Grobman theorem or linearization theorem. So, this tells about this theorem is about the local behavior of the dynamical system in the neighborhood of a hyperbolic equilibrium point. Basically, the theorem states that the behavior of a dynamical system near a hyperbolic equilibrium point is qualitatively the same as the behavior of its linearization near its equilibrium point, provided that no eigenvalue of the linearization has its real part equal to 0. So, if we have a hyperbolic fixed point, then according to this theorem, so this linearized system behavior and the original system behavior will be similar. So, if we can linearize near the equilibrium position and study its stability, so this will give the local stability of the system. So, for finding the global stability of the system, so one may use this Lyapunov method. So, here some definitions also we can see. So, what is hyperbolic fixed point? When all the eigenvalues of this Jacobian matrix have non-zero real parts, it is known as hyperbolic fixed point. So, if all the eigenvalues of A have negative real part, then it is known as sink. The sink may be stable focus if it has non-zero imaginary parts, and if it is a stable node. So, either it can be stable focus or it can be stable node. So, in case of stable focus, so it has non-zero imaginary parts, and in case of stable node, it contains only real eigen. So, it contains only real eigenvalues, that means the imaginary parts are 0. So, in the eigenvalue, so in case of a sink, so all the eigenvalues have negative real parts, and if it contains non-zero imaginary part, then it is stable focus, and if it contains only real eigenvalues, that means the imaginary part is 0, then it is known as stable node. So, the sink is stable. So, and source, if one or more eigenvalues of A have positive real part, then it is known as source. So, here the system is unstable and it may be unstable focus or unstable node. So, in case of unstable focus, so it will have non-zero imaginary parts, and in case of unstable node, it will have, so it will have 0 imaginary parts. That means, all the eigenvalues will be real, and some of the eigenvalues will contain positive real parts. So, in that case it will be a source or the system will be unstable. Similarly, saddle point, when some of the eigenvalues have positive real parts while the rest of the eigenvalues have negative real parts, then it will be a saddle point. So, in case of the source, if one or more eigenvalues have positive real part, this is source, and in case of saddle point, when some of the eigenvalues have positive real parts while the rest of the eigenvalues have negative real parts. So, the systems can be called marginally stable if some of the eigenvalues have negative real parts while the rest of the eigenvalues have 0 real parts. So, these are different terminology for the equilibrium points. So, we have this hyperbolic fixed point when all the eigenvalues of A has non-zero real parts, then it is hyperbolic. So, if it has 0 real part, if some of the eigenvalues have 0 real part, then it is called non-hyperbolic fixed point. So, in case of the hyperbolic fixed point, we have sink, source, saddle point, and based on these things, so we can study the equilibrium system. For example, already we have seen in this example x double dot minus x equal to 0. So, if we have x double dot minus x equal to 0, so by putting this part equal to 0 which varies with time. So, the equilibrium position is x equal to 0, that is the origin. So, x equal to 0 is the equilibrium position. So, in this equilibrium position, one can see that this point is a saddle point. So, later we will see how we have checked its eigenvalue to find whether it is a saddle point or sink or source. For example, this equation, so this x double dot minus x equal to 0 can be written by using two equations. So, this is second order differential equation, that thing can be written as a first order differential equation. So, let me put the first equation x dot equal to y. So, the second equation will be this second order differential equation can be written by using these two. So, x dot equal to y, and I can write this x double dot that is equal to y dot. So, y dot will be equal to, so y dot equal to this x. So, x double dot equal to x, so y dot equal to x. So, these are the two equations, these are the two first order equation one can solve to check whether the point is a saddle node or whether the point is a saddle node point or not. So, in this case x dot equal to y and y dot equal to x. So, one can write this A matrix as, so A matrix can be written. So, for the first equation x dot equal to y, so this is x equal to 0, x there is no x term, that is 0. So, this is 1. So, and in case of the second equation one can write this is equal to 1 0. So, this is the equation, as this is a linear equation. So, one can find its delta x dot will be equal to delta y and delta y dot equal to delta x. So, A can be written so in this way, or A can be written by del f by del x equal to 0 and del f by del y equal to 1. Similarly, in the second equation del f by del x equal to 1, and as there is no y term, so this is equal to this. So, from this A minus lambda I, so A minus lambda I, determinant of A minus lambda I equal to 0, where lambda is the eigenvalue. So, from this one can obtain this lambda. So, this is lambda A minus lambda. So, minus lambda. So, this equation. So, from this equation one can write. So, this is minus lambda 1. So, then this is 1 minus lambda. So, A minus lambda I. So, determinant of this thing. So, from this one can get this lambda square. So, lambda square minus 1 equal to 0. So, if lambda square minus 1 equal to 0, so from this one can find the roots. So, from these roots, so lambda square minus 1 equal to 0. So, by finding the roots one can study, so whether the point is stable, marginally stable, or it is a saddle point or node point. So, in this case also one can similarly proceeding in this way writing the set of first order equation. So, one can check whether the system is a stable node, whether the system is a. So, this spiral means this. So, the spiral out or in. So, this is a stable spiral, as all the points are spiraling inside this is a stable point. Similarly, this is a center point. So, in this case also, in this example, x double dot plus x minus 0.1 x cube. So, which is similar to that of a Duffing equation equal to 0. So, one can see this point is a saddle point, this point correspond to the center point, and this point correspond to the saddle point corresponding to this maximum. The saddle point correspond to the maximum potential energy and center correspond to the minimum potential energy. So, as another further one example, one can take this y dot simple example, y dot equal to lambda y. So, the equilibrium position y t will be equal to. So, in this case y dot will put this y dot equal to 0. So, y t can be written equal to 0. The stable equilibrium position. So, for stable equilibrium position, so we can write. So, our equation reduces to. So, as y dot equal to lambda y. So, we can find. So, this a minus lambda I. So, we can write a. So, if lambda less than minus lambda less than 0. So, the point will be stable, and if lambda greater than 0. So, it will show the system unstable. For example, in this case the solution is y t equal to as dy by dt equal to lambda y. So, y dot equal to this, or dy by dt equal to lambda y, or one can find this dy by y equal to lambda dt. So, by integrating one can find this ln y equal to lambda t. So, from this, so one can write. So, y equal to some constant. So, some constant, let C 1 or C. So, e to the power lambda t. So, this is the solution. So, in this case, if lambda is positive, then exponentially it will increase, the response will exponentially increase and it will becomes unstable, and if lambda is negative, exponentially it will decrease to make the system stable. So, depending on the value of lambda, so one can find these things. So, in this case, so if we use our original method, that is y dot equal to, in this case, so our A matrix, to obtain this A matrix, one can find this del f by E. So, this is, so our f x m. So, in this case our f x m equal to lambda y. So, del f by del x, or we can write. So, for x, instead of writing x, as our variable is y. So, we can write this is y m, and so in this case we can write del f by E. So, del f by del y. So, a equal to lambda. So, a equal to lambda, or I can. So, from this one can study. So, one can find the eigenvalue, and from this eigenvalue we have seen that if lambda less than 0, it is stable, and if lambda greater than 0, it is unstable. So, let us take this another example, that is Duffing equation. In case of the Duffing equation, either we can directly solve this equation to find its stability, or we can use the Potter's equation using method of multiple scale. For example, if one use method of multiple scale, then one can obtain a set of reduced equation which can be written in this form. So, a dash equal to minus mu a. So, let us take the Duffing equation in this form, that is u double dot plus omega 0 square u plus 2 epsilon mu u dot plus epsilon alpha u cube equal to epsilon k cos omega t. So, here this is the epsilon mu u dot, that is the damping, and this is the nonlinear term, and this is the forcing term. This part is the forcing term. So, here we have assumed the force to be very small, that is why we have used this bookkeeping parameter epsilon. Omega square is the square of the frequency, and mu is the damping factor. So, in this equation the solution can be written in this form, u will be equal to a cos omega 0 t plus beta. So, where this beta or gamma can be written as sigma t 1 minus beta. So, here sigma is the detuning parameter. So, sigma is the detuning parameter to express the nearness of this parameter with respect to the excitation frequency omega. So, in this case this equation, the reduced equation can be written A dash equal to minus mu A plus half k by omega 0 sin gamma, and this A gamma dash equal to sigma A minus 3 by 8 A cube plus half k by omega 0 cos gamma. So, these two are the reduced equation obtained by using method of multiple scale. So, using method of multiple scale, so one can find these two reduced equation. So, now for steady state motion, so as they are not function of time, so this A dash and gamma dash will be equal to 0. So, one can write the equation in this form. So, mu A will be equal to half k by omega 0 sin gamma, and A sigma minus 3 by 8 alpha by omega 0 A cube. So, this will be equal to minus half k by omega 0 cos gamma. So, from these two equation, right hand side squaring the right hand side and adding these two. So, one can obtain the frequency equation. So, the frequency equation will be in this form. So, mu square plus sigma minus 3 by 8 alpha by omega 0 A square whole square into A square equal to k square by 4 omega 0 square. So, this is the frequency response equation. So, from this, so one can find the amplitude. So, we have seen the solution of this equation equal to A cos omega 0 t plus beta. So, this amplitude A and frequency they are related by using this equation. So, in this equation we have this sigma which is detuning parameter. So, that can be that shows the nearness of this omega. So, omega will be equal to omega 0 plus epsilon sigma. So, from this equation, from this frequency equation, so one can plot the response. So, this equation can further be written using this sigma. So, sigma will be equal to 3 by 8 alpha by omega 0 A 0 A square plus minus k square by 4 omega 0 A square minus mu square to the power half. So, mu square to the power half. So, using the sigma and A equation, this equation is a quadratic equation in terms of A in terms of sigma. So, that is why solving this quadratic equation. So, one can obtain the sigma, but one can numerically also solve this equation. This will be a sixth order equation in terms of A square, as we have A square here, square term is there, another A square is multiplied outside. So, this is a sixth order equation in terms of A or a quadratic equation in terms of sigma, as it is easier to solve this quadratic equation. So, one can write, so one can solve this quadratic equation to write sigma, otherwise one can use the numerical method, some numerical method to solve this equation for A. So, now solving this equation one can obtain the response. So, the response A and sigma one can obtain. For example, for alpha greater than 0, the curve will looks like this. So, in this case each point on this curve, whether these points or this solution what we obtain. So, this is for A, and one can plot the gamma equation also, So, this is A versus sigma. Sigma is the detuning parameter, A is the amplitude, similarly gamma is the phase, and with respect to sigma one can plot, and here one can see that the plot will like this. So, in this case, for corresponding to a particular value of A, for example, sigma equal to for this sigma value. So, this is A value and this is the sigma value. So, this is the gamma value. So, corresponding to this A and gamma value. So, one can check whether this point is stable or not. So, to check the stability of this point, so one can perturb the solution, that means taking this A equal to A 0 plus, let me take this is equal to A 1, A 0 plus A 1 and gamma equal to gamma 0 plus gamma 1. So, one can perturb this equation, that means this equation A dash and gamma dash equation can be perturbed, and by substituting this A and gamma in that equation, one can write this, one can obtain the Jacobian matrix. So, this Jacobian matrix can be written in this form, that is minus mu minus A 0 into sigma minus 3 alpha A 0 square by 8 omega 0. So, this is 1 by A 0 into sigma minus 9 alpha A 0 square by 8 omega 0. So, this is minus mu. So, now one can find the eigenvalue of this Jacobian matrix corresponding to this value of A and gamma, and study the stability, whether this branch is stable or unstable. And after studying the stability of each branch, one can know, so whether the corresponding response is stable or unstable. So, one can note in this case, so up to this sigma, so the system has a single branch, but after this value of sigma, so one can have 3 solutions. So, out of these 3 solutions, some solutions may be stable, some may be unstable, and one can study the stability by finding the eigenvalue of this Jacobian matrix. So, these eigenvalue, so for example, in this case, so by putting this A minus lambda I equal to 0, we will have the equation lambda square plus 2 mu lambda plus mu square plus sigma minus 3 alpha A 0 square by 8 omega 0 into sigma minus 9 alpha A 0 square by 8 omega 0 equal to 0. So, for steady state motion, so the steady state motion will be unstable. So, if we have this term gamma equal to sigma minus 3 alpha A 0 square by 8 omega 0 into sigma minus 9 alpha A 0 square by 8 omega 0 plus mu square less than 0. So, one can see the book by Nafe and Mook, nonlinear oscillation. Nonlinear oscillation to know more about the stability of this type of system, nonlinear oscillations. So, one can obtain the stability. So, from this equation, so when lambda is less than 0, the real part of lambda is less than 0, then the system will be stable. So, from this one can solve and see this equation, or find that if this term less than 0, then the system will be unstable. So, in this way one can study the stability of the system. Sometimes this Jacobian matrix may have distinct eigenvalues, or sometimes they may not be distinct. So, depending on these eigenvalues, so one can study the stability and one can obtain the bifurcation diagrams. So, let us to study the global stability. So, one can use this Lyapunov stability method. So, instead of going for the linearization technique, so one can use Lyapunov stability. So, in case of the Lyapunov stability, so one has to develop the difficulty of this Lyapunov stability is that one has to develop a function, Lyapunov function, to study the stability of the system. So, in case of this Lyapunov stability, so according to this, a stationary solution y is said to be asymptotically stable if the response to a small perturbation approach 0 as the time approach infinity. An asymptotically stable equilibrium is called a sink. A stationary solution y is said to be stable if the response to a small perturbation remains small as the time approaches infinity. Otherwise, the stationary solution is called unstable, as in this case the deviation grows with time. An unstable equilibrium is also called a source and is an example of repeller. So, in this case, so one has to find one Lyapunov function and one has to check whether the system is asymptotically stable or unstable. So, in this case, so this is the equilibrium solution. So, near this equilibrium solution, if we perturb this equilibrium solution, so if it remains within a bounded region, then it becomes stable, and if with time it approaches this equilibrium position, then it is asymptotically stable. So, let us take one example. So, let us take the van der Pol equation. So, according to this Lyapunov method, so we have to take one Lyapunov function which is a positive definite function. So, if its derivative becomes negative definite, then the system is stable, otherwise the system is unstable. So, for example, taking this van der Pol equation, let us take the van der Pol equation, that is x y double dot plus y minus epsilon y dot q by 3 minus y dot. So, this is equal to 0. So, in this case, so this is the well known van der Pol equation. So, one can write this equation by using a set of first order equation. So, in this case, first order equation will be, let me put this y dot equal to x. So, the second equation becomes x dot, that means y double dot, x dot equal to minus y plus epsilon into x cube by 3 minus x. So, this is equal to 0. So, in this case the equilibrium points will be x dot equal to 0, and by putting this x dot equal to 0 and y dot equal to 0. So, we will find the equilibrium position by putting this y dot equal to 0. So, x equal to 0 is we obtain x equal to 0. Now, by putting x dot equal to 0 and x equal to 0. So, we obtain the equilibrium. So, the equilibrium point, so the equilibrium point is x equal to 0 and y equal to 0. So, we have to check whether this equilibrium point is stable or not. So, we can take a Lyapunov function. Let us take a Lyapunov function b equal to half x square plus y square. So, this function is positive. So, this is a positive definite function. So, this is always positive for all values of x and y. So, now we can, from this equation, so we can write this v dot. So, if you differentiate this thing, so this v dot equal to half into 2 into x dot plus half into 2 into y dot. So, this becomes x dot plus y into y dot. So, this thing can be written. So, from this we know what is our x dot and y dot value from this equation. So, now substituting that thing, so we can write x into, so v dot will be x into, so for x dot one can substitute, this is equal to minus y plus epsilon into x cube by 3 minus x. So, into minus x plus y into y dot. So, y dot equal to x. So, this becomes, so minus x y plus epsilon x into x cube by 3 minus x. plus, so this is x y. So, minus x y plus x y cancel. So, this becomes, so this term can be written as minus epsilon x into x becomes x square minus x fourth by 3. So, this becomes minus epsilon x square minus x fourth by 3. So, this term is as x square and x fourth. So, they are positive. So, this term can be, so this term will be always negative. So, from this we have seen that this point, so we will have a stable point at x equal to 0 and y equal to 0. So, let us see, to obtain the solution. So, one can use this numerical technique. Using MATLAB also one can find the response of the system. For example, in case of this Duffing equation, so one can write this program using this ODE45. So, for ODE45 one can use the simple commands. So, T y equal to ODE45. So, this is the function I am using FF2. So, this is the function. So, where these first order differential equations, two first order differential equations are written, that is dy1 equal to y2 and this dy2 equal to minus y1 plus y1 cube minus 2 mu y square. So, this is for the Duffing equation. Similarly, one can write, so similarly one can write for the Van der Pol equation, and by using this command one can find the response of the system. So, here the response are plotted, that is y1, y2, y1 and y2 are these displacement and velocity. So, one can obtain the phase portrait. So, also one can obtain by plotting this t and y1. So, one can obtain the time response. So, from the time response and frequency response one can study whether the system is stable or unstable. So, one can find the response. So, from this response also one can study whether it is decreasing, exponentially decreasing, or it is decreasing and finally, it is stable in this case, or from the phase portrait. So, this is the time response. So, one can plot the phase portrait also. So, in case of the phase portrait, so starting from this initial position, if the response grows, that means with time it increases and increases. So, then it will be unstable, or if it, so starting from this position, let me start from this position. So, in this case, if the response decreases and finally comes to this position, so this position is a stable position. So, if one plot, so for this case the phase portrait is this. So, this shows a stable point. So, by using these numerical methods also one can find the time response, phase portrait, and from this time response and phase portrait one can visualize whether actually the system is stable at the equilibrium position. So, this is the equilibrium position corresponding to x equal to 0 and x dot equal to. So, this is x equal to 0 and x dot equal to 0 is the equilibrium position. So, it shows that this equilibrium position is stable. So, from this time response one can understand whether the response is stable or not. So, this is also a periodic response. In case of a periodic response, the phase portrait, so the phase portrait is periodic. So, one can use these methods, this time response and phase portrait, to visualize actually whether the system is stable or not, and by finding the eigenvalues from the Jacobian matrix one can theoretically or analytically predict whether the systems will be stable or unstable at that point. So, already we have seen the bifurcation. So, bifurcation points, and in case of the bifurcation point, so we know we have two different bifurcations. One is continuous bifurcation and other one is discontinuous bifurcation. In case of continuous bifurcation, we have static bifurcation and dynamic bifurcation. In case of static bifurcation, we have the saddle node bifurcation. pitchfork or symmetry breaking bifurcation and transcritical bifurcation, and in case of the dynamic bifurcation we have hop bifurcation. So, today class we will basically study about the saddle node and pitchfork symmetry breaking bifurcation. And okay. So, in case of the saddle node bifurcation, the normal form for a generic saddle node bifurcation fixed point is, so x dot equal to or x dot equal to f x mu, or this thing can be written. So, this is the generic form, that is mu minus x square, or one can write also this generic form x dot equal to, so x dot equal to mu minus alpha or mu plus alpha x square. So, in this form also one can write the equation. So, in this case alpha equal to minus 1. So, it becomes mu minus alpha x square. So, for the saddle node bifurcation point, now one can find the Jacobian matrix as x dot equal to minus mu x square. So, as we have this x dot equal to minus mu minus x square. So, in this case this equilibrium point becomes, putting this x dot equal to 0. So, equilibrium point mu minus x square equal to 0. So, from this one obtain this x square equal to mu or x equal to plus minus root mu. So, corresponding to positive and negative value of mu, so one can plot the response plot. So, this is the x mu plot. So, one can see that corresponding to different value, positive value of mu. So, this is positive value of mu, and negative, for negative value of mu one can see. So, from this equation, so if mu is negative, so this is imaginary. So, the root will be or x will be imaginary. So, that is why it is not plotted, and for x after x equal to 0, mu equal to 0 only we will have the solution. So, here one may note that before mu equal to 0, so there no solution exists in this case, and after this mu equal to 0, so we have two branches of solution. So, this point mu corresponding to 0 is a bifurcation point, as here there is change in the number of the solutions, and also we can see that the quality of the solutions, that is the stability type of the solutions also changes. So, this is for a one dimensional equation. So, for two dimensional equations also. So, this is example of a two dimensional equation. So, in this case one can find the Jacobian matrix. So, after finding this Jacobian matrix, so one can obtain the eigenvalues of this Jacobian matrix, and one can observe that this part of the solution is unstable and this is stable. So, as it is unstable at this position, so when one sweep up the frequency, so at this position the system will show a jump up phenomena, and further increase in this frequency it will follow this path. Similarly, during sweeping down the frequency, that means if you decrease the frequency, so one can follow this path. So, one can follow this path during sweeping down, and at this point, so it will jump down. So, one can observe this jump up and jump down phenomena at these bifurcation points. So, similarly, one can check this pitchfork type of bifurcation. So, in case of pitchfork bifurcation, the normal form of the pitchfork bifurcation is mu x plus alpha x square equal to 0. So, if we write this mu x plus alpha x square equal to 0. So, this is the alpha x square equal to 0. So, in this case our equation, one dimensional equation becomes x dot equal to mu x plus alpha x square. Now, putting this x dot equal to 0. So, we have this equation. So, from this equation we can find the equilibrium position. So, in this case to find the equilibrium position, this will give, so mu plus alpha x equal to 0. So, if I will take this alpha, so depending on different value of alpha, so we can have a set of curves. So, let us take alpha equal to -1. So, this curve is shown in this figure. So, corresponding to alpha equal to -1. So, we have this equation x dot equal to mu x minus x square. So, in this case our Jacobian matrix. So, to obtain this Jacobian matrix, so we will find this del f by del x, the matrix with del f by del x as it is one dimensional. So, we will have only one. So, this becomes mu plus, so this becomes mu plus 2 alpha x. So, as our a minus lambda I, so we have to make a minus lambda I equal to, so a minus lambda I, determinant of a minus lambda I equal to 0. So, in this case as only we have one term. So, we can write this mu plus 2 alpha x minus lambda equal to 0. So, our lambda becomes, the eigenvalue becomes mu plus 2 alpha x. So, as alpha equal to -1, so we can write this lambda equal to mu minus 2 x. So, as lambda equal to mu minus 2 x. So, depending on the value of mu, we can obtain different value of x, and we can study whether the branch is stable or unstable. So, in this case we have seen this trivial solution. So, one solution is, so x into mu plus alpha x equal to 0. So, the equilibrium position becomes x equal to equilibrium position becomes x equal to 0. So, that is the trivial solution, and also we have a non-trivial solution, that is mu plus alpha x by putting this mu plus alpha x equal to 0. So, we have, or this putting this alpha equal to -1. So, mu minus x equal to 0 or mu equal to x. So, we have two points, one is x equal to 0 and another one is mu equal to x equal to mu. So, we have these two, x equal to mu. So, now we can plot. So, from this plot we can see, so we have this trivial branch. So, in this trivial branch becomes stable. So, if the Jacobian matrix has negative real parts, similarly, so here one can observe that at this point, at this, so from this branch, so if one solve this equation, so one can find the solution. Okay, so in this case for Pitchfork bifurcation, it will be x dot will be equal to mu x minus x cube. So, the previous things what we have taken this example mu x plus alpha x square equal to 0. So, we have two solution, that is x equal to 0 and x equal to mu. So, this is the example of this transcritical bifurcation. So, in this case this is mu x minus x square. So, this is the x equal to 0 line, x equal to 0 line, and x equal to, the second one is x equal to mu. So, this is x equal to mu line. So, x equal to mu, this is x equal to 0. So, this is Pitchfork bifurcation. So, and in case of the, this is transcritical bifurcation. So, in case of the Pitchfork bifurcation, so mu x minus x cube will be equal to 0. So, x dot equal to mu x minus x cube. So, taking this x common, so we have mu minus x square equal to 0, or x equal to 0 is the trivial state response. Trivial state response, and mu minus x square equal to 0 or x square equal to plus minus root mu. So, x equal to plus minus root mu. So, from this x square equal to mu or x equal to plus minus root mu. So, this is non-trivial response. So, in this case, so one can find the Jacobian matrix from this. So, the Jacobian matrix A will be equal to, so this becomes mu minus 3 x square. So, now by substituting this value, for example, taking this x equal to 0, that is for the trivial state. So, one can observe this branch to be stable. this branch to be stable and this is unstable and this is stable. So, at this point, so at this point one can observe that the response, before that one has 3 solutions. So, out of the 3 solutions, the upper branch and lower branch were stable and the middle branch is unstable, and at this point, so this becomes, the trivial state become unstable and one has 2 solutions. So, out of before this thing, out of these 3 solutions, these 2 are stable and this is unstable, and after this one has a unstable solution. So, this point, so where it tends to jump from this position to this upper one is known as subcritical Pitchfork bifurcation point. Similarly, while sweeping down this thing, so we have this supercritical Pitchfork bifurcation point. So, next class we will study about the Hopf bifurcation point. One more example one can see, so where this one can apply the stability analysis. For example, one can refer this paper by Kaur and Dwivedi, International Journal of Nonlinear Mechanics, 1999, page number 315 to 515 to 529. So, this is where the nonlinear dynamics of a slender beam is studied. So, in this case, the equation can be written in this form, and here 2 mode interaction has been taken. So, to study the principal parametric resonance case by taking this phi external frequency nearly equal to twice the first mode frequency and using this detuning parameter sigma 1 and sigma 2 as internal resonance is taken. So, this second mode frequency was taken thrice the first mode frequency. So, this is for internal resonance and this is for external resonance. So, in this case, so one can get, by using this method of multiple scale, so one can get a set of 4 first order equation. So, previously we have seen 2 equations, now one can take a set of 4 equations. Now, by perturbing these things, so one can obtain the Jacobian matrix and one can study the stability. But in this case one can see that while perturbing, some of these perturbation will vanish for the trivial state. To overcome that thing, so one can use this transformation. So, here Pi equal to Ai cos gamma I and Qi equal to Ai sin gamma I has been taken. So, then one can write this equation by writing this transform form in terms of P and Q. So, one obtain these 4 equations. So, using these 4 equations, so now perturbing these 4 equations, one can find the Jacobian matrix and study the stability. So, in this case one can plot this A1 and A2. So, these here A1 and A2 have been plotted. So, A1, A2 have been plotted. So, by solving the set of equations, by substituting this P dash Q dash P1 dash Q1 dash P2 dash Q2 dash equal to 0, and one plot this response. So, after plotting this response, one can study whether the branch is stable or unstable. So, by using the Jacobian matrix. So, in this way one can study the stability of a system. So, here one can observe, so this point at the Pitchfork bifurcation point. So, this point is a saddle node bifurcation point. So, later we will see that in this curve there are also some points which Hopf bifurcation points. Those things we will study in the next class. Thank you.